on. 5, 4, 3, 2. Hello, Bobby or Robert Brooke.
Hello.
Hello, my friend. Thank you for the podcast. Thanks for coming on my podcast. The name of the podcast is Brain, Hope, Reality, PTSD, not PTSD. I am undergoing a continuous battle or trying to change the name PTSD to PTSD, post-traumatic stress injury, being a biologic change. So the reason I wanted to have you on the podcast is because I'm very fascinated with epigenetics in general. I had a degree in molecular genetics from 1980 from Northwestern. I never heard the term epigenetics. And I found out about 10 years ago, and I was listening to David Sinclair talking about longevity, and he was talking about Harvard clocks, which is, I assume the first epigenetic clock that was developed. And being a simpleton that I am, I reached out to Dr. Harvard, and he connected me to you since you clearly work with Dr. Harvard at UCLA. And you and I are doing a study right now, checking out epigenetic change that happens from PTSD, post-traumatic stress disorder. We'll stick to standard term. And at least there was one study that showed appropriate psychiatric care for PTSD, if successful, can reverse aging. And I was very interested in that because I work with special forces quite often. And special forces people age quicker than an average individual because of severity of battle and severity of PTSD. Thus, we'll talk about that study. And also it's going to be the big reveal. I'm 65 years old. How old am I based on epigenetics? I think it'd be fun to talk about it. So with that intro, I said, if you don't mind just telling you about background, and maybe you can talk about where epigenetics come from, the history of it, and maybe we'll dig into it. Maybe you can explain it and for simple terms, which, I consider myself somewhat scientific, but it's still quite confusing. So you're right, my friend.
Right. Well, great. Well, yeah. Well, thank you, Dr. Lipov or Gene. So yeah, no, it's been great getting to know you as you've been launching your clinical studies, and yeah, it's an impressive kind of team that you've put together to manage them, and a very important condition and kind of area to focus on. So I'm really happy that I could be a part of it through the Clock Foundation, through a nonprofit that I started with Steve Horvath and spun out his epigenetic aging technology from UCLA. But yeah, no, I'm happy to help with that trial and to be here and try to tell you about epigenetics.
Thank you. So when
also
time. Did you hear my question?
I did not hear your question.
Sorry. My question is, when did the epigenetics become actually a science, and where did it come from? I remember there was a study in Danish people who were being starved by the Nazis, and it led to diabetes, I think. I think that's the origin, but I don't know. I'm just
interesting. Yeah, and that may be related to kind of the concept of epigenetic inheritance. That's kind of where a lot of people hear about epigenetics initially are these kind of transgenerational effects, where if a family or a population experiences famine or some stress or trauma, it can have effects not only on them, not only on their kind of kids, but even kind of their grandkids, kind of for generations to come. And that's this concept of kind of epigenetic imprinting, where it can affect your genes, your gene expression, and ultimately your body. But yeah, and I guess kind of backing up epigenetics, the term epi means above, so it kind of controls the genome, and so it controls gene expression in your cells and in your tissues. It kind of dictates what cellular state. So it kind of determines if a stem cell becomes a fibroblast, or it becomes a neuron or a muscle cell, and then it helps control cellular state as you age.
So can I ask you a simple question? So let me see this. I'll tell you how I understand epigenetics now, because one of the things about somebody like yourself, since you live in that space, to you it's pretty obvious, but most people probably not that obvious. So let me see if I got the basics right. So DNA is basically a molecule, dual strand, of course, that has a code. The only way to permanently change the code is to have a mutation that will change the code, and that's it. So each gene can be either turned on or turned off, right? So methylation, you can change the genes, and that can turn on or turn it off. And so based on that, and the reason, the way I understand it, and again, my particular interest is sympathetic system, fight and flight system, and the way the nature designed us, it's a way, so trauma or external experience can activate or deactivate certain genes in your DNA. Right?
That's exactly right. That's exactly right. Yeah.
And it's reversible.
Yeah, and it's reversible. I mean, that's what, yeah, and like along those lines, the epigenome is, it controls which genes get turned on and off, and it can be influenced by your environment. So if you experience trauma or kind of famine or like your body responds to that, and so for instance, like when people experience famine, like if there's no food available, people often different orient, like they kind of see it where caloric restriction occurs, and right. And people devote more, your body devotes more resources to kind of preserving it, and not as much to reproduction, and that's an effect where it actually extends lifespan and many different mammals and also invertebrates. And but it's just an example of your body kind of responding to the environment, and there are epigenetic mechanisms kind of at play. But along the lines of like the fight or flight system and kind of the sympathetic and parasympathetic nervous systems. And also provide some background on epigenetic clocks. So kind of what epigenetic clocks are basically these predictors where you can think about your genome that is just decorated at different positions with these methylation sites that get turned on or off, and they also change reliably with age. So when you're in youth, there's certain genes that get turned on to promote development, and as you age, there are other genes that certain switches get turned off or on, and that kind of lead you into middle life and eventually into late life, and so there are certain sites that change very reliably with age, and what Steve Horvath did at UCLA was he discovered that these patterns of methylation changes, you could use them to predict somebody's age. And so, for instance, with a blood draw or a saliva sample, using epigenetics, you can predict somebody's age to within about a year or 2 years. And
can I push on that for a second? Let me just, and again, I speak hopefully for the audience that doesn't quite understand what that means. So let me see if I understand what that means. So when somebody says, based on your DNA, and you can run a test, I think it's 1,100 alleles, which is 1,100 different places, then somebody who is 50 years old normally and will live to an X amount of years, right? Somebody who's had a hard life, who is chronologically 50, but they had a very rough life, it could be physiologically 70. So they're much older based on the DNA analysis. And the reason it's important to know that is that the 70-year-old, biologically 70-year-old, will die sooner than the guy who's 50-year-old biologically, right? That's basically the plan. And that my reading it is, I read some you guys' articles, and it looks like there is a very high predictor, especially cardiovascular and place like that.
Yeah.
Because most of the people in Western countries die of cardiovascular events. I think that kind of makes sense. So biologically, it's an amazing concept that as somebody ages, you can have, as you said, a predictable change, but some people go at a much quicker pace. In fact, you look at people who, let's say, heavy smokers and they had a very hard life. You look at their twin brother or sister, and you look at them, they look totally different. And you can see a difference, like a significant physical, and people go, well, you look so much younger. There's actually a lot behind that, right? There's a biologic difference. Is that correct?
Right. Yeah, and epigenetic clocks, they started as just an objective marker of age, and so it's just this is just a blood draw or a saliva sample, and the original clocks developed in the Horvath lab. They just predict the age of any human cell type or tissue. And but like you mentioned, I mean, where it gets exciting is that epigenetics is first that they're modifiable, and where it's relevant is that you can track that over time. And so when you're taking a treatment like a putative longevity protocol or treatment, you can take that test before and after and understand if this very objective measure of age has been influenced by it. And so you can start to understand, do these treatments really affect the fundamental biology of aging? And one point that was related, with the original Horvath clock, it specifically targets 353 different sites across the epigenome. And what people are starting to do now is to kind of tease out, like, what are each of those sites doing, and like the biology of epigenetic clocks. But what's is interesting is I think 30 to 35% of them are sites around the glucocorticoid receptor and glucocorticoid signaling. So very related to kind of stress control. And but yeah, in newer versions of these clocks have been developed, such as GrimAge, which is even better at predicting future health span and lifespan. So, but again, these are objective biomarkers where you're submitting a blood sample. It's predicting your epigenetic age, and that's being used as a proxy of your biological age. And like you mentioned, if you're 5 years younger on your biological age than your chronological age, you're doing well. You're kind of healthier than would be predicted for your age. And in a variety of diseases, measures like GrimAge are shown to be accelerated. So, for instance, in major depression, people with GrimAge are accelerated by about 2 years. In combat veterans with PTSD, they're shown to be accelerated by about 2 to 3 years. And and people are just now starting to use these measures in trials, like you're doing, to really very quickly understand, is this treatment really effective for the population, and can it target epigenetic aging?
Well, the part that I find most interesting as a clinician is, in the old studies of anything, is you need to, since human beings relative to rats are long-lived, so you don't have to wait for people to die to figure out, oh, this drug really makes you live longer. Like rapamycin is one of the drugs you may be familiar with. It has been used for longevity. It's a fascinating drug. I've been taking this for a year at least.
Yeah.
And then, so the point is, you can actually do something about it, and you can actually test it. You don't have to wait for an organism to die.
That's been traditionally kind of the challenge with any drug or treatment that's kind of preventative medicine or trying to target the biology of aging is just the trials take way too long, right? You're doing a preventative medicine study and you've got to wait 7 years or 10 years to see if it's effective. And, and people don't want to wait that long. It's hard to get people to comply and even participate in trials like that. So epigenetic clocks are very enabling in that they enable this, again, objective biomarker that you can use and test whether a treatment works within 3 months or 6 months or a year. And, and it's awful. I mean, there are other biomarkers out there that we pay attention to in trials that are very important, like functional outcomes. Like if you're doing a PTSD trial, I mean, there are simple surveys you give to people that you start to understand like their quality of life. And if you're doing a cognitive, I mean, you can do a cognitive test. You can do functional tests for people to look at things like VO2 max, or you can look at leg strength. And again, there are simple measures we use in trials like a sit-stand test or a walking speed test, which are very informative. But often a lot of these tests, when you're using them in a younger population, kind of a healthier population, like what's an issue is that they experience what we call like a ceiling effect. So, and again, I'm talking here about traditional measures of frailty, of physical frailty that you can measure with like grip strength or walking speed or some cognitive tests. They're really designed to detect frailty in a pretty old population, and so it's people that are kind of in their 70s, maybe even their 80s, that are really experiencing kind of pretty rapid decline at that point. Now, when you enroll people who are healthier, who are younger, maybe in their 40s, 50s, healthy people in their 60s and 70s, the issue is that on these traditional frailty measures, they ace the test. They get a perfect score. And so the tests just really aren't sensitive enough to detect those changes in the aging process that occur earlier in life. So that's been a big advantage of epigenetic clocks, and then also again, going back is epigenetics are modifiable. So, I mean, that kind of begs the next question. Well, what is there that can influence them? What can what type of treatment can be effective? And there are studies that have looked at like stress control can reduce epigenetic clocks. Diet, some like Mediterranean diet's been shown to benefit epigenetic aging. Vitamin D treatment in vitamin D deficient people reduced epigenetic age. I've also been involved with a study called the TRIM trial and the TRIM-X trial that's focused on immune system regeneration, where we repurposed a cocktail of approved drugs to try to prevent immune system aging in healthy older people. And that treatment's been shown to reduce epigenetic clocks by a few years. And so for us, it's exciting. It's kind of inspiring that there are these approved drugs. There are these treatments that are already out there that are available, people can access. And now we have these objective biomarkers that we can use on a practical time frame within trials to test whether or not a treatment's effective. So so we've been very busy kind of using them, and we've done kind of over 100 collaborations and studies over the last 2 or 3 years. So it's been kind of a frenetic pace for us, but yeah, it's definitely an exciting time for the field.
So I have two questions. So question number one is, how long do you think it takes from, let's say there's a drug X that's effective in age reversal or prevention, like rapamycin, let's say. But have there been any studies on rapamycin and epigenetics? Do you know?
There have been preclinical studies that show that rapamycin reduces epigenetic aging, but I'm not aware of clinical data that
No, I'd be curious if there was anything, and if you can send me any of those preclinical, it'd be amazing to read.
Mm-hmm. Yeah, there's definitely.
Yeah, I I haven't been able to see. I'd love to see it. Number two, how long is it, from your perspective, how long does it take to change when you can actually see a measurable difference? So let's say somebody's a heavy smoker, fat, all the terrible risk factors. Poof, next month, they stop smoking, they lost weight, they're doing intermittent fasting, and they're exercising appropriately. How long would it change? How long does it take to change epigenetic code between the two, the same individual? Over what period of time does it change, you think?
Yeah. Yeah, I mean, I think it's I'm sure it's dependent on on specific treatments. And so, for instance, like smoking, there are just like epidemiological studies look at the risk of smoking and find that when people stop, there still is this residual risk for many years. It could be 10 or 15 years before the increased risk really goes away with them. And so so I'm not aware of data looking specifically at kind of epigenetic aging with smokers, but a couple other areas are like stress control.
Yeah, let's say that one.
Yeah. In that, I've seen very short-term studies that where there's a benefit, and this is like a month or 2 months.
Oh wow!
And they're showing an improvement with it, and there are studies that look at vitamin D. I believe that was also a pretty short-term study, maybe a couple of months of treatment, and there was a reduction. That was in deficient people, so that was not in healthy kind of older people. Now, treatments like the TrimX treatment for thymus regeneration, that's a longer term, that's a longer time frame. It's a year-long treatment, and there are some indications that it may take 6 to 9 months, kind of at least, for that to have an effect. But yeah, I mean, I think with each of them, also we need to. It's great that we can get short-term data, but we also do need to pay attention to whether or not a treatment has durable effects. So if you're seeing an improvement that's sustained, it's gonna last for a year or 2 years after you stop. We don't want it to just be a short-term blip. We want it to be a long-term kind of beneficial improvement, beneficial change.
So what do you think of doing a reveal of my chronological age versus biological age?
Yeah, sounds great. So yeah, you submitted your own blood sample for testing, and we ran the GrimAge marker, and this was just based entirely on your blood sample with no other inputs, and you were predicted to be 52 and a half years old based on GrimAge. Now, how old are you?
65.
65. So that's a very good score. So, I mean, 12 and a half years less than your chronological age is, that's quite a, so for instance, with GrimAge, the risk with it, if you're 7 to 10 years accelerated on it, you would have double the mortality risk for somebody your age. So conversely, if you're 7 to 10 years younger, you have half the mortality risk of somebody your age. So, I mean, you have, like probably 75 or 80% lower based on this measure mortality risk than what would be predicted for your age.
I appreciate it. Well, I do try. I've changed my diet. I lost weight. I take rapamycin and metformin, the two drugs which are predicted to be helpful. That's an amazing. I didn't know that until just today, actually. So thank you for that information.
Yeah, that's an impressive score.
Thank you. So I'm trying to. I tell my wife I'd like to operate into my 90s. I have a big mission. There's a lot of people with PTSD would like to help, and there's a lot of things to do. And I'm looking forward to doing amazing things with you and epigenetics, because there's so many. It's interesting, the stress thing. That's the whole concept that you can change your DNA, either for good or bad, and that just to me is a mind-boggling concept. right? It's just amazing. But if you think about it, I'd like to see what you think of this concept. The way I try to focus, why did God made this for us? Why is there a biological evolution? So let's say you are a caveman and you're being chased around by a tiger. And then if you're being chased around by a tiger, in order to survive, you need to have hypervigilance. You want to minimize the amount of reproduction you're having because you're vulnerable. And it takes energy to produce reproduction and things like that. And then you want to pass it on to your offspring so they can survive as well. So if you look at this, my particular history, my father had horrible PTSD from World War II. His squadron of 10,000, 100 made it home. So he gave that DNA to me. That made me much more likely to develop PTSD. And I looked at and the reason I got very serious about my health is because I had chest pain, which really turned out to be nothing. But then I did calcium scores, and I had a very high calcium score when I was 30. So I was on my way to be checked out, like in my 50s or 60s. So at the time I was 40, I really became I was fat. I wasn't taking care of myself, too much stress, all of that. So actually, that was my rationale. But it would have been interesting to measure my GrimAge because I think I was about 4 or 5 years older than my biological age then, and how it can change over time. To me, it's a very enabling concept that it's possible because a lot of people go, well, I'm fat, I can't help myself, I can't do this. You actually can do a lot of things which are very basic.
Right. Yeah, I mean, that reminds me of what happened with Steve Horvath. So, I mean, he I guess 2 years or so ago now, he was enrolling as a control in one of our trials, and he had one of those coronary artery calcium scans, and he had a significant score, and he was freaked out about it, and I mean it does give people. I mean I think that it's right on your coronary artery, right, with a plaque. I mean, they call it the widowmaker kind of plaque. So it is a very serious kind of test. When you get it's kind of a scary biomarker. But
you can do something with that. But let me ask you one question: what was his epigenetic score like? Was that
So what he did was, I mean, it's similar to what he changed his diet. Right. So he started taking a statin. And then he was on some controlled treatments as part of our trial, but he improved his score significantly by about 5 years within a year or a year and a half.
So my only recommendation to him, if he is up to it, is take a lot of K2, vitamin K2. It sucks out calcium from the coronaries. I don't know if he's doing it. So you can buy K2 and D3 on Amazon anywhere. I would highly suggest doing it daily. If he's not doing it, he should be doing it for sure.
Interesting. Yeah.
Right, statins and so LDL is the one that's the biggest predictor for that. Not total cholesterol, LDL. So my LDL was like 120. So between statin and the new injectable drugs, mine is now at 30 for the last 2 years.
Interesting. Yeah, we do that testing with Dr. Matt Budoff in LA at Harbor UCLA Medical Center. He's a preventive cardiologist, and he's done several trials. I haven't heard about K2 being tested there, but they've used a lot of pharmaceuticals, a lot of drugs, I think PCSK9 inhibitors and statins, and where they didn't find an effect, by the way, on the calcium score at least. But they looked at, there's like a type of Japanese garlic they used. It was in a firefighter study, and that was one supplement, one treatment that seemed to reduce the score. But I'll pay attention to K2.
Look at can you send me that garlic study? I'd be very interested in Japanese. By the way, the latest kind of talk about Japanese. So wasabi, the Japanese horseradish, I call it. Have you seen the latest study that came out as far as cognitive improvement? If you take it for 3 months, it's a significant impact.
Yeah.
But try to find horseradish in this country. Wow. Wasabi, I went everywhere, including a Japanese store.
Yeah.
It has real wasabi powder.
Yeah. Is it difficult now, or is it
Finding?
Yeah.
It's
Or
almost
you're in Chicago though, right? Yeah, and maybe in LA, is it easier to find?
I don't know.
Or is there a shortage? Is that what you're saying? There's a shortage of it?
No.
Oh.
Anytime you buy wasabi, like wasabi powder,
Mm-hmm.
sushi restaurants, Japanese stores from Japan, right? It says wasabi in it, but it's really not. It's all horseradish.
Okay.
A lie. It's all a lie. It's fascinating. Anyway, but yeah, check it into K2. I think it'd be interesting. So, yeah, well, do you do like CRP studies also? C-reactive protein?
Yeah, we do CRP.
Yeah, because like mine has been 0.3 for the last 5 years, which is consistent with the finding, right?
Yeah, that's better than mine. Yeah.
You're young. You have plenty of time to do things.
Yeah. And what did you do to reduce CRP? Either the K2? You think that helped with that?
No. K2 doesn't do anything CRP. So CRP demonstrates inflammation. Mm-hmm. So I think Mediterranean diet, stopping meat is huge. Meat is pro-inflammatory. Yeah. Like meat, like red meat we're talking about. I think fish, I eat tons of oil, avocado oil, tons of it. No fried foods at all, because fried foods cause anything pro-inflammatory is a bad thing for you. Mm-hmm. But I think Mediterranean diet, as you said, intermittent fasting, I think is a really very powerful technique. So if you have a significant CRP, you may want to think about the plunging thing. Ice plunge, I have no interest in that, but some people like that. But anything anti-inflammatory. But it's interesting, for example, I don't know if you saw my paper about immune impact of stellate ganglion block. So the stellate is what I use to reverse PTSD, right? Sympathetic.
Right.
So the first time stellate was ever used was in France for asthma. So there is direct connection from stellate ganglia to the bone marrow in the thymus. Mm-hmm. So it's been used to treat ulcerative colitis symptoms in China. What's interesting there, they measured CRP, interleukin-6, which is another inflammatory marker, and they saw a significant drop in interleukin-6. So the point is, anxiety and things like that does much more to you than you think. So to me, PTSD potentially can increase cancer load by dysregulating immune system, because immune system leads to scavenging. Scavenging takes out tumor cells, right? So that's why people kind of go, well, mental health is no big deal. It is a very big deal.
Yeah.
It increases the chance of heart attack by a factor of 2 and things like that. So it's no joke.
Yeah. Yeah, and that's definitely consistent with what we say, and with the major depression studies and PTSD studies. When you're accelerating on average, GrimAge by 2 or 3 years, that you're kind of you're measuring the blood, you're measuring the immune system. It's a big part of it, and if you're kind of accelerating the aging of your immune system, especially in older people. Most people when they're in their 60s or kind of in their 70s is when they experience an immune system collapse, and so you're just kind of accelerating, like towards that point with people. So I absolutely agree. Kind of some of these basic steps can really do a lot to slow or prevent people from it can slow the onset of that immune system collapse in older people. So right. Yeah, that's a big kind of aim of the TRIM trials that we're conducting.
I think it's great. Well, anything you can send to me, I would love to read. I'm fascinated by this whole concept, and I even though I'm a clinician, I'm trying to understand all of this stuff, and it's starting to make more sense to me. But the ultimate goal is in 2023, we can actually measure things, right? So the more you measure it, you can actually do something based. Instead of drugs people think are amazing, they're actually not doing anything. Or maybe
that's right. Yeah. I think that's I missed a little bit of what you said there, but yeah, I mean, we have these tools available. We have these objective biomarkers. We have other very reliable kind of ways to track whether a treatment's effective or not. Like and people want to get in, people can easily get involved these days. Like you can participate in these studies often from home. I mean, you might visit somewhere to enroll and to get started, but then you're at home most of the time. They can be pretty convenient for people. And so we can tell pretty quickly whether or not a treatment is effective or not, and it's not, we're no longer in this period where people just argue for years and years about, this treatment or that treatment and, without any data to support it. Right. We can cut through a lot of that noise and just do simple studies, do simple trials pretty quickly and know, know with a lot more confidence.
So I try to keep our podcast relatively short, but I think it's fascinating. I really appreciate. I have absolutely loved working with you, and I'm looking forward to publishing, because my hope is, frankly, is the way people always say in the military, at least in the U.S., where the special forces go, the Army goes. Where Army goes, society goes. So wouldn't it be amazing at the end of the study we can say pretty significantly that with PTSD, you're aging fast. We can actually, so that's something to think about. So stellate, something I do, and I call it SOF method. So we've seen significant improvement of PTSD symptoms clinically, but it's self-report. But you can actually say, it's like before you're 3 years older than your stated age, your chronological age. Biological age was 3 years old, but now it's 3 years younger. That would be, I think, a mind-blowing concept, because it still hasn't percolated. The whole concept that mental health can actually make you age seem to have escaped people's notice, even though there have been a number of studies showing that the chance of heart attack is twice as high with somebody with PTSD versus someone who does not have it.
Yeah,
right? That's a known fact. But
right. Yeah, and what you mentioned, results like that can change the conversation. So I mean, and a lot of people, they don't talk about certain topics because they don't think it can be treated. Like the situation can't change. And I mean, like we mentioned at the very beginning, changing PTSD to PTSI, or just providing some path that shows people how to improve it. I think that's kind of critical. Like you get even studies that with as few as 20 or 30 people, when you can show a profound impact on them, they really can kind of impact the field and how medicine's practiced. So for me, I mean, it's really exciting to be involved, and innovative physicians like you are just so critical. And and there's I'm really excited to see kind of what will come with this study, and many more to come. So I look forward to working with you into your 90s, like you say.
Here we'll talk about the same thing.
Yeah,
but we get bigger, and we'll see. What I'd like to have is a chart, like a big chart, how many lives we've saved and how many people made them younger, or not age as quickly. Wouldn't that be amazing? What a thing to do.
Yeah, there's just there's so many exciting studies to do, and I mean, you can just feel it that so many people want to be involved, either participating in a trial or help coordinating them. And I mean, so many people kind of just recognize that, we now have these tools that they just simply weren't there 20 years ago or 30 years ago. It was an incredible opportunity.
Right. 10 years ago, nobody was really, it was just starting, but it wasn't easily available, and you couldn't run them. It was hyper expensive. So, anyway, I'm going to leave you on that note. I really appreciate you coming. It's a pleasure chatting with you. I feel like we've known each other for a bit now, even though it's only been a year, but I think we're going to do some big things.
Absolutely. Yeah.
Thank you, my friend.
With you. All right. Take care.
Thank you.
All the struggle and pain I leave behind.